The focus of this video is going to be the hip assembly and its mobility. For context, this is where the assembly fits within the robot general assembly. The three axes of motion sit within the torso in a motor assembly which also acts as a large portion of the torso structure and the actual visual shell. This is the basic shape of the robot torso. The three axes shown here are the axes for yaw or medial lateral rotation, roll or leg adduction abduction, and pitch or leg flexion extension. The initial axes positions were chosen roughly. As the mechanism was constructed, they were adjusted to incorporate the parts. The starting specs for roll and yaw were plus or minus 5 degrees. I don't know how dependent bipedal movement relies on a wide range. Pitch motion was kept large, as this is really leg motion outside the torso. I expect it to be more critical for motion, and also being outside the torso allows it to be less constrained. I've since seen a paper with values for a human, which has a much larger range than what I've achieved, but don't think it's a true direct comparison, but interesting nonetheless. I used the dynamic model from the leg as the foundation to run initial calculations for the adduction motors. Reusing the 8115 would have meant a large torso width increase, which is way beyond what I wanted to have. The dynamic model assumes the leg is fully extended to provide the worst case moment of inertia for the load on the motor. This was then swept through the range of motion from max external to max internal and vice versa. The peak force is basically the weight of the robot, and the peak torque is a little above 6 Newton meters. With the torques produced, I ran through the list of steady wind motors and narrowed down the options. The aim was to get a small package volume while still reaching the torques needed. I chose to not run the same analysis on the yaw axis. How the leg is positioned around the axis should give it a moment of inertia that is substantially smaller than for the roll. If the motor works for roll, then it should be suitable for yaw. This means I can have one less unique motor to work with, hopefully simplifying the electronics and software later. These are to show which motor achieves which motion, and which are the 4310 motors and which is the 8115. Adduction moves the whole assembly, yaw swivels the internal bracket, then pitch moves the leg in the resultant direction from the roll and yaw motors. These videos show a few different angles of what pivoting looks like with the parts. Adding the leg on does mean there are a few clashes in different places depending on the leg position. I do want to dig in deeper to understand what changes I can make to either the torso, the leg, or the connection between to minimize these clashes, and also how I can accommodate for the clash risks in the software. For now, it's good enough to keep moving forward with. One of the initial questions was, what order do the roll, pitch, and yaw occur? Pitch was easy and already accounted for in the leg design. I was originally planning to have just pitch and no yaw or roll. The choice of yaw and roll ultimately came down to the motor geometry, the surrounding geometry, and the impact to it, rather than the mechanism itself. The pitch motor and leg assembly are positioned quite inbound, which means the yaw and adduction motors are pushed out further from the orthogonal axes, leading to increased displacement with a change in angle. Shifting the leg outward does make the robot quite wide, unless I can slim down the leg width. The video left shows how much the yaw motor is rotating with roll motion. This motion is still clear of both the torso sidewalls, but also the upper torso structures, if only just. There is a risk of colliding with the opposite yaw motor, as the motion envelope does break through the center plane, so one to keep an eye out for within software. The space it is moving in is less valuable for designing with, mostly due to the shape and access to it. On the other side, we can see that the neutral position of the roll motor is already at the edge of the torso, and even locally pushing out the torso. With even 5 degrees of motion, it would lead to a wider torso from the needed clearance, and also risk the usability of the volume at the rear of the torso, which in my opinion is much more valuable to work with. Ideally, both yaw and roll motors are shifted closer to their orthogonal axes. This would require adjustments to the leg and pitch motor positioning, so one for a future version unless I can or need to include it with other changes. Cutting through the middle of each mechanism, both use a bearing and a bushing to act as a pivot opposite the motor drive. The bushings are separate parts to allow for the possibility of assembly. A spacer is also added between the yaw motor and hip bracket, again to allow assembly. Assembly of the left torso motor begins with the assembly of a hip bracket, subassembly, a hip adduction pivot subassembly, and then the main assembly, which both subassemblies get assembled into. The images and videos will show the left-hand side, but the structure on the right is just a mirror of this. The design of the full torso will be covered in a future video, so click subscribe if you want to make sure you catch it. The leg is connected to the robot through the femur inner onto the pitch motor. If you have any questions, ideas, or areas you want me to cover, throw them in the comments below. At the moment, the leg needs to be somewhat assembled on the torso. The femur inner is attached, then the rest of the leg is attached to the femur inner. I expect this is going to be rather annoying or lead to me running tests with just the femur inner attached, but probably both. Ideally, I can turn this into some form of quick release so the legs can be taken off and on easily for tests and development and probably repairs. For the rest of the project, prototype parts have arrived to build up a left hip motor assembly. Software to test the new 4310 motors has been started. This is based on the previous 8115 software. A basic URDF has been made for the existing biped design as well.